Hello everyone, I hope you all are doing well. So in this session, I'm here with the CFD analysis on bus using SolidWorks flow simulation. So I have taken three configurations into account, that is with mirror, with cam mirror, without mirror. Let's get started with this. We'll see how exactly we need to deal with this and how to find out the drag force and the coefficient of drag. So I'll name the project as CFD, and you can change the inner system for velocity to kilometers per hour because I'm referring the same thing. Analysis type is external, and the gases I'll take it as air, and I'll keep it as default. The velocity along x direction I'll mention it as 100 kilometers per hour for the commercial vehicles. Okay, so this is the computational fluid domain. So I'll just set it up by using a computational fluid domain, and which is using the drag method. So the flow domain should be quite bigger so that you can just check out the flow exactly how it is happening. So you can use the front view and you can align the same thing like this. Okay, yep. So after that you can just use the mesh. At the moment I'll just take the fine mesh. I'm not going to deal with any of the coarse mesh. Later on I'll just make the changes into the mesh. So in automatic, I'll keep it level 7, and I'll activate the advanced channel refinement. If you want, you can even use the refinement level to something 2 or 1.5 is fine. Yeah. So this is the basic meshing which I'm using. Now the goals which I'm looking for is mainly the drag force. Here the drag force should be considered along x direction, remember that. So there might be a slight confusion in the previous sessions as well. So if you want to take the drag, it should be along x-axis. If you want to calculate the left force, it should be along y-axis. Clear? Yeah. So the static force I'm going to consider at the moment. So only these three I'm looking for. Now I also need the coefficient of drag calculation. So for that you need to add the equation. So this is the equation, that is 2 times of force into rho into v square into area, that is velocity square into area, frontal area. Okay, so 2 times of goal is the f of x I need to take. So you can just click on this goal, add goal, and from here you can choose the goal. Okay, f of x2 is added there, and the same rho density, and these are the velocity values in meters per second. It is 27.878. Yeah, can take it. Same thing here, and the frontal area you need to calculate it. So by using the SolidWorks evaluate tool, that you need to do it. Later on I'll showcase how to just calculate this one. That is just a approximation. Okay, I'm not taking the exact areas into account. This is just an approximation. So once you define these all the boundary conditions, just go ahead with the just running the simulation. So that is CFD analysis. So it will take some time to just give you the converged results. Yeah, so you could see the iterations. It is around 161 iterations. You got the results here. You can activate the cut plots. You can have the planes wherever you want. So let me just place it exactly at the middle. So you can even take it wherever like the location you're looking for. So the results I'm looking for is the velocity distribution. You can check velocity along x-axis. So this is how it is. Let me just take the overall velocity. Yeah, so this is the velocity distribution. So you can just change your vector formats and the other stuff. So right now I'll just see how the pressure distribution is. This is fine. Streamlines you can activate the values you need to define. Here I'll take the velocity plot into account, and here the vorticity can just increase the number of vortices. Okay, so now the surface slots, you just need to define what results you're looking for. Let me just take the pressure, use all the faces, and if you want you can activate the vectors and streamlines, not needed at the time. Yep, so this is the surface plot. Okay, so now you can even activate the isoflots to just check how the velocity or the pressure is distributing with respect to the speed which you have defined, that is velocity. So you could see, I'll just add the transparency up to zero point 0.5 is fine. So this is the velocity level. Here you can just increase or decrease. So let me just drag it up to 100. You can even manually enter it here. So I'll take it 100. Could see exactly at the 100, there is a slight disturbance to the flow. Like you will face more drag for this. So you can even check with the 80 kilometers per hour or 90 kilometers per hour. This would be a smooth flow of the turbulence and all. So there won't be much uh, disturbance to the vehicle. Okay. So like this, you can use the iso plots to iso surfaces to deal with this. So now these are the flow trajectories. You can activate the rectangle and you can define the number of points. So you can just take it your values and you can customize your rectangle by just using the drag options. Okay, like this, the pointer you can just adjust it to just save the time. So or else it will just if you have the system with the low specifications, it will take more time to load these all the stuff. So yeah, you can just hide the floats which and all you're not looking for. Let me just hide this cut float. Yeah, so this is how it's gonna look like at the final stage. Now coming to the results, so which we have extracted, that is the drag and the coefficient of drag that we'll see. Before that, let me just animate this. This is how the flow trajectories looks like. Okay, so if you want to analyze it, you can just check the same thing. So just simply hide it at the moment and I'll go with the goals and I'll just plot them so for your convenience. So equation goal and the drag force, the coefficient of lift and coefficient of drag and drag force. You could see this is the just approximation. Okay, this is simple analysis which I have taken into account. So you can just activate the history plots as well. Now it comes to the refinement and all, so that I'll do it now. Before that, instead of calculating for only one, I have the three models as I said. So with mirror, without mirror and the cam mirror. So here I want to analyze this all the models and I want to check out the drag force for each and every model. So without camera, sorry, without mirror and with mirror, how much is the drag, and with cam mirror, how much is the drag force is acting. So with respect to that, I can choose which is the best one. Okay, let me just do the same thing. So I had already created the configurations for you guys, so you can check. Let me just showcase the same thing. Now I'll just showcase the CD formula. It is, could see the values. Before that, I'll showcase how to deal with the frontal area. So you can activate the measure tool from the evaluate and just select the faces. These are the faces which I'm going to consider for the frontal area approximation. Okay, so here you need to do it manually. So you could see the values. So it is 10.62. The same value you can enter it there for the frontal area, the CL formula. So these values should be appropriate or else you won't get the results properly. Remember that. So the formula is CL, which is equal to 2 times of drag force into divided by rho into v square into area, that is density into velocity square into frontal area. Okay, so this is with cam mirror, that is camera. So here you can check the area. So I'll just consider these. And the value you could see, that is 10.66. You can take the same value and enter the value into the CD formula. It is fine, no need to change here. Yeah, so once it is done, so we can again check with the one more model, that is with mirror model. So here again, let me just check the frontal area. It is 11.6. So let me just verify the same. If you have the drag force, you can use the formula and you can calculate by yourself. As we are using the software, we don't want to use the like manual calculations here. So I'm just referring these things approximately for my convenience. Okay, I might need to take these areas as well. Okay, and this is the value, that is 10.68 value. I need to change it there now. Okay, so these are the values. We are done with this. Yep, so you can just save this model. To run these all the three analysis in one shot in SolidWorks flow simulation, we have the advanced option. Okay, that is the batch run. Okay, and we have the compare results tool, so which will also help you to compare the results without making any presentations and all. So that also I'll showcase in this particular analysis. So let me just run this all the analysis in one shot. So for that, you can just simply switch to the flow simulation tab. From there, from the results drop down, you will get the batch run option. Okay, so if you want to mesh it again, you can just use it solve and new, and just simply use the number of instance in a simulation. So I'm gonna run multiple, so it's gonna take some time to just evaluate your all the results and get to the results. Now you could see I'm only concerned about the coefficient of drag and the drag force results for all the three, and while calculating you could see the uh, results monitor. Yeah, so the results are ready now. You can just go to the preview and just load them by just right clicking on the results and load results. Okay, yeah, so to just preview the results, you can simply go to the results and use the compare, and here I'm concerned about all the three projects and I'm looking for the goal plots. So just if you click on compare, it will give you all the three values. Okay, for no mirror you could see the CD value is 0.25, and with cam mirror it is 0.53, got reduced, increased, and even here with mirror it is 0.53, so 9 it is. So CD will increase with respect to the mirrors. So here could even see the drag force, that is comparatively increasing for each and every configurations. So this concludes that the model with cam mirror is better than the model with normal mirror, so that we can just save the drag force, and this we can implement practically. So these are the few plots. You can switch to the summaries and chart options and tables. So this is one way to deal with this. This is about the results comparisons. So we do have the comparison to the all the three flow trajectories and the all the plots which you had on club plots and iso plots and even all the plots. So let me just showcase the same. So if you just use the compare tool, it will give you the same comparison. You can use this particular preview into the big screen like this, and you can check the these are the plots, the cut plots, the velocity plots we can say, and you can even switch to the flow trajectories, and this is the maximum values. Here the flow trajectories are like this. You can able to compare the results. So these are the SolidWorks flow simulation advanced tools. If you want to use it, you can use it. Yep, that's all about this session. So we have gone through the CFD analysis on bus, that is Volvo bus, by using the without mirror, with cam mirror, and with normal mirror, and we have concluded that the cam mirror is having the less drag force and the comparatively good drag coefficient, so that we can practically implement. Yep, that's all about this session. Thank you guys, stay tuned, bye everyone.